All right. Hello, everyone. Welcome to the April 2025 LINCC Tech Talk. My name is Colin Ryan Chandler, and our co-host is Mi Dai. We are both LINCC Frameworks project scientists. I'm at the Dirac Institute, University of Washington, and Mi is at the University of Pittsburgh. These tech talks include presentations and demonstrations that showcase work done by the broader Rubin software and archives community with the goal of further enabling LSST science. And unlike traditional talks you might hear at a conference, tech talks highlight the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present and learn about and discuss efforts of interest in the analysis of LSST data. Tech Talks are delivered virtually every second Thursday of the month at 10 o'clock a.m. Pacific. Today we are joined by Matt Holman, who will talk about LAYUP, an orbit fitting package that is part of the LINCC Incubator program. And Matt is a senior astrophysicist at the Harvard Smithsonian Center for Astrophysics. He's the former director of the Minor Planet Center and specializes in the study of long-term solar system dynamics with a special interest in distant bodies like trans-Neptunian objects and centaurs. For the talk, please ask questions in Zoom or in the hashtag LINCC Tech Talks channel on the LSST DA Slack. On Zoom, you can type questions into the chat or raise your hand. And as a friendly reminder, these talks are being recorded and they will be posted on YouTube with the consent of the speaker. So with that, Matt, please take it away.
Thanks, Colin. Thanks for the opportunity to speak to the group. I wonder if I can ask a question first, because I like to try to keep these things interactive. So is there a way for, well, let me just encourage people to raise their hand. So if they do that, Colin or you or somebody else, can you let people speak, or do people have control of their mute?
People do have control over their own microphones, so we can leave it to your discretion.
Okay. So so as Colin said, I'm leading one of the LINCC Frameworks Incubators, and this is about developing a tool for orbit fitting at LSST scale. There are a long list of people who are involved. Highlight Meg Schwamb, who's acting as a project manager, sort of basically trying to keep us all in line and moving in one direction. But there are people at a lot of different institutions, and we're fortunate to have Drew and Max and Wilson as the software engineers for LINCC helping us out. Okay. So Meg gets the credit for all of the cool slides, and I get the credit or responsibility for the boring ones, and I'll leave it to you to decide which is which. When I looked up, orbit fitting images in Google, this is what I got. I didn't realize there is such a thing as an orbit fitting and that they come in 2-packs. But it would have been a lot easier if we had just ordered them instead of having to write a proposal. But really what we're talking about is this kind of thing. This is what Rubin and what various other ground-based surveys have been doing for decades, looking for asteroids. And this is the kind of the first stage where I'm going to start asking questions of people. So this is a sequence. You see the stationary objects in the background; those are the stars and galaxies, and the moving object is an asteroid. So what do we know from just looking at those sequences? What have we already learned? So if no one raises their hand, I'll make call and answer.
I see the asteroids moving.
You see the asteroids moving. Okay, so I will posit that you've learned 4 things, at least 4 things, maybe 5, but let's concentrate on the 4 things. 4 numerical quantities. What might those be? There's a
position and rates.
Yep, 2 positions and like an RA index and 2 rates. You know those I'll say incredibly well. So 2 of the quantities incredibly well, and I'll say 2 of them kind of okay. What are those? How did I break those up?
Times. We know times really well.
We know times really well. We also know, like, the initial position. We know where the thing is, RA index at that time. We know, like, to a couple tenths of an arc second. The rates of motion, we know pretty well, but how well we know the rates of motion is really dictated by how long we've looked. I'm guessing that this sequence of images spans about an hour. So, and we see probably 30 arc seconds of motion in that hour. So that gives you a sense of, we have pretty good measurements of the angular rates, really good measurements of the individual positions. So what do we not know from these images directly? What can I can't, there are a couple of things, like for an orbit, I'll lay it out there. There's, you need 6 quantities, because you have 3 components of position, 3 components of velocity. So we have 4 things we know really well. What are 2 that we don't know?
Distance and velocity
Yep.
on the distance.
That's right. Distance to the object from the observer or from any other place, and that radial velocity. Those are not known. We have to infer those. That's what orbit fitting is all about, and that's what Gauss was, working on when he initially solved this problem. So there's this nice clean separation between what we know, like, where it is in time and the rates, and the things we don't know, which is the distance and the radial velocities. So we're trying to build a really good tool to do this orbit fitting, and this is not a new problem, right? As I said, Gauss was the first to really tackle this. There are some really good software packages out there. There's Bill Gray's OrbFit. There's Gary Bernstein and Kushalani's Outer Solar System Orbit Fitter. There's the University of Pisa OrbFit. I'll note that the Bernstein's code is also called OrbFit, so I just forbid anyone to name anything else OrbFit, and I think we've already violated that within this project. But okay, so there's the Pisa OrbFit and there's Orbit OpenOrb. These have been really successful because they're fast, they're reliable, they're pretty easy to use. They allow astronomers to read in various data formats and get an orbit out. So why don't we just use one of these? So that's another one. I'm asking you the question, so you can posit answers. Why are we having a LINCC Frameworks Incubator for this? Meg's the ringer.
Because they're not easy to use anymore, or they're not open source and they're not able to handle it at the level we need for Rubin. So love Gary's code, Bernstein Kushalani, but is it something that I can use currently? No. And so that's, I think, one of the things is scaling these up, and also some of these others that are not necessarily as open, getting them to where we are today with computers and Python.
Yeah, exactly. And so on top of easy to use, several of them are written in Fortran, and I'm not old enough to be adept at Fortran, and I'm one of the oldest people on the call probably. And I think OpenOrb can be accessed with Python, but the other ones, really cannot. Some of them have really only one person contributing, maybe 0 people contributing. So they're not necessarily open source, or if they are, they're not maintained, they're not easy to use, and they're not really in modern codes. So we're going to try to address that. And so that's what the LAYUP project is about. And there are several different components. This is a slide that's not as cool as the others, but it is due to Meg, laid out the components of this. And the main one that I'm going to focus on, can you see my cursor on the screen?
Yes, we can.
Okay, so I'm going to mostly talk about the orbit fit component of this, but there are several others. Like any package, you've got to get started up. You have to get it initialized so you can use it. And then there are a bunch of downstream tools, and I'll talk about those too. You can interrupt me at any point and ask questions, because if you don't, I'll keep asking you questions. So, okay, this is an officially cool slide. So there are, as I pointed out, there are a number of different components. There's one for reading in the data and any other auxiliary information that's necessary to make the orbit fitting work. There's initial orbit determination. There's the orbit fitting algorithm, and then there's all the downstream output stuff. And I'll go through. Do we have a question ready? Okay. Yeah, all right. So there's bonus points if you can name all the robots. Anybody can, you can name them in the chat. So let me talk about the input reader. You're going to see these same needs in pretty much each of these components. It's got to be super fast and efficient. It's got to be able to handle Rubin data at all scales, and not just Rubin data, data from all different types, from all different platforms. It's got to be user-friendly, and maybe just not user hostile. But it's got to be able to be used by planetary astronomers who are looking for moving objects, but it also has to be able to accommodate the advanced users who are going to do fancy things. So examples of the kind of input are really what you might imagine: time, RA-DEC, astrometric uncertainties, or if you're doing looking for faint objects, you might have time and RA-DEC and rates of motion and uncertainties. If you have radar, you might have those range data like time, round trip time information from radar. You might have Doppler velocities. So we need something that will take all of that in and convert it to something that we can consistently use within the code. And that's basically, the stuff we need is where is the observatory? What are the observations, say like unit vectors? We need things put into a frame that makes sense, or everything's consistent, likewise sky plane rates of motion. And there's a whole bunch of different formats. There's the old MPC's 80-column format. There's the astrometric data exchange standard format, and various other things that may come from Rubin itself or other sources. And we are working to make sure that we can accommodate all of those. And then initial orbit determination. So I'm again, this has to be super fast and efficient. We've written the first version of this in C, C++. It's got to handle lots of data and handle, kind of various different forms of data. And then what this thing does is comes up with an initial guess for what the orbit is. So, okay, here are the questions for you. Like, why do we need initial orbit determination? Aren't we just doing orbit fitting? Can't we just jump to the final answer? Can't we just like flip to the back of the book and see what it says back there? Anybody willing to give it a shot? Oh, Gary, man, wow, I'm in trouble.
Do you want to be in a linear perturbation regime for the rest of your code? Is that it? Like close?
Yeah, you want to be close, right? You want, it doesn't necessarily have to be in a linear perturbation regime, but it really helps. So another way of saying rephrasing that question or the answer to it is that orbit fitting is, there's a huge phase space. And what we're trying to do is find the orbit that goes through a sequence of observations as a function of time. And if you're not close to the right answer, you're typically not going to you're not going to converge to an answer at all. So you want to be, pretty close to the right answer and then go from there. And Gary is overqualified to ask that question because he's provided one of the solutions. So the first solution is Gauss's method. And this is the oldest one there is, and there's different versions of that, but it's essentially taking 3 observations that are spread out some way in time. And that's kind of a question, is like, how should they be spread out? And what it does is it can find there's an exact deterministic approach to getting a solution to that problem. Well, actually, you'll get up to 3 solutions when you do that, but it's, take 3 astrometric observations and you get it answers out, and you can use those as the next step for improving the thing. So that's one solution that I credit Kevin Napier for coding that up in Rust. Gauss, of course, gets credit too, but there's an interesting story here. that we are coding things for the LAYUP project in C++. Kevin is really good at Rust, so he handed his Rust implementation of Gauss's method to ChatGPT and asked it to give him a solution in C++, and he handed that to me. And I looked at it and I thought, huh, this doesn't seem right, but it's pretty close. Let me, see what I can, clean this up. And it was right. It was totally right. I was like, I learned some formalism in C++ that things I had not, known before. And so that's, kind of amazing to me. So the second solution is something that Gary is responsible for, and that is, instead of taking 3 observations, it's taking a bit of data in a tangent plane set of observations over, it can be some sequence of time, but it is a solution that is linear. You can get a linear least squares solution to it and then proceed from there. Once you have an initial orbit fit, you need something to improve the fit. And this is, again, the same stuff. It has to be really fast and efficient. We're writing this in C++. It has to be able to handle lots of data, different types of data. And the basics are that we start with some initial position and velocity. We will numerically integrate that position and velocity to the times of the observations, compare, compute where we would see that model object from the observatory at that time. And I'll come back to a question about that. And then ultimately compare those model observations to the model observations to what is actually observed, and then do a nonlinear least squares. And I'll talk a little bit more about that. The tools we're using are the rebound and assist numerical integrators. I wrote assist. Rebound is written by Hanno Ryan and his collaborators, and has components from Sorka in it. So as I said, there's the pieces of this are the inputs really are the initial guess and some reference time, a set of observations, and what we call data weights, which are the uncertainties associated with each of the observations. And there's the output is an updated orbit and a covariance matrix with how, what are the uncertainties in the orbit, and in our case, it's the position and velocities and how they're correlated, and residuals as for each of the observations, and then also a list of outliers, things that are so far off the model that they would corrupt the solution if we don't reject them. Just to elaborate, just to provide a little more detail, as I said, this is based on rebound and assist and numerical integrators stuff that I wrote, and there's something I've said here, a light time correction loop. Gary doesn't get to answer this one, but what do I mean by that? What is light time correction?
You have to adjust for the amount of time. Since you're dealing with distance, your observation is some minutes or hours behind where the actual object is at the moment that you observe it. So you have to take that into account.
Yeah, that's exactly right. So it's 8 minutes per AU. So it can be, a typical main belt asteroid might, where we're observing, when we observe it, we're observing where it was, say, 30 minutes ago. And that has to be taken into account. And I put the word loop in there because the solution to it is iterative. You don't know the answer. That light time correction ends up on both sides of the equation, and you have to basically say, let me take a guess and how far it is away. Let me compute where the approach is to assume that light travels, immediately to the observer, and use that to compute the distance, and then use that distance to compute how long the light time was, plug that in, and do that a few times until it converges. The next component is, well, we've written this in C++, mostly because of the eigen linear algebra library. It's a header-only library that's very efficient and well well tested. And so that's what allows us to do, break up all the pieces for the nonlinear least squares pretty easily. And okay, so this package is called LAYUP because of rebound assist layup. I have a kid who likes basketball. Then once we have the result, we need a bunch of output functions. And as it says, this part has not been decided yet. But again, it has to handle Rubin scale data, provide all kinds of formats for what people want, allow the precision storage of the values. And there's various interactions here. There's the input. Once you read in the input, it could go to the initial orbit determination. All right, here's the quiz. Who are the different transformers? I know I've stepped on one of these more than once in my life.
The yellow one's Bumblebee, red one's Optimus Prime.
Excellent, excellent. Full points. So let's talk about who are the target users for this, orbit fit package for LAYUP. It is the Rubin solar system team. It might be postdocs who are using KB mod or some other shift and stack, techniques for looking for faint objects. Could be any graduate student who's trolling through data, who needs orbit fitting and needs orbit prediction routines. It might be the graduate student looking for distant planets. Anybody who needs follow-up. Might be people who are looking for non-gravitational forces on comets. Any amateur who's looking for particular objects, maybe potential impactors. So let's talk a little bit about how would the Rubin team use this. So the components of LAYUP can be, you can directly plug in data that would, say, be coming from Rubin in whatever internal format. So this LAYUP will, provide a local orbit fitting solution so that things don't necessarily have to be handed off to the MPC and come back to get their answer. Again, the same thing could be used with for other routines like KB mod, because what's I think different LAYUP differs from a lot of the other packages in that it can take not just right ascensions and declinations, but rate, RADEC and rate observations, which is what you'd get from the data you get from shift and stack routines. Another component is predict. What predict is just once you have the solution, an orbit fit solution and a covariance matrix from that, you'll want to use that. And basically, if you hand it a time, an orbit, covariance matrix, and the position of the observatory at the time, you'll get back the observed unit vectors, sky plane rates of motion, range and radial velocities, and covariance for each of those. And again, who are the users for predict? It really is pretty much any astronomer who's looking at moving objects who might turn to JPL in other times to get this data. Just like anybody who's looking for positions of objects on the sky as a function of time in various forms. There's another component. I'm not going to spend much time talking about this, but visualization is a big part. And so the LAYUP project is building a bunch of visualization tools so that you can have interactively look at the results of the orbit fitting. And another piece of this is tools in order to not just look at the results, but say select out outlier observations and things like that and see how the orbits are affected. This is one of the challenges of the LAYUP project is it needs to be written in a way that individual users can interact with the data and do small runs, but it also has to be able to scale up to millions of orbits like we expect from Rubin. Again, like the use case is pretty much any solar system astronomer who is looking to make, explore their data or make figures for their talks or papers. So LAYUP convert is a component just for converting the input and output from different formats. So most of this stuff is, we're not inventing anything here, but just providing tools for the community. And I think I'm going to stop there and let people ask some questions.
Great. Thank you very much, Matt. We do have some time for questions, quite a lot of time for questions. So please feel free to ask questions in Slack, chat here on Zoom, or you can raise your hand. Yeah, let's give folks a second to collect their thoughts. Go ahead, Kostya.
Do you implement your own nonlinear least squares fitting algorithm, or do you use some library?
Could you repeat the question?
Do you implement your own nonlinear least squares fitting code, or do you use some library for that?
So I wrote a Levenberg Marquardt fitter, but it's actually just like 4 lines of code with Eigen. It's really not hard. I mean, Eigen does all of the matrix manipulation stuff, so it was relatively straightforward to write a Newton's method and then make that a little more general. And that's I can show you that if you're interested in the details.
Okay. No, I was just interested in how sophisticated your nonlinear least squares should be. I'm happy to know that it is just longer Marquardt.
Yeah, it's really not all that complicated. So and part of that is because the assist integrator, assist is basically an open source version of the integrator behind JPL Horizons. So I worked with people to make sure that all of that is correct and all of the terms in the equations of motion are correct. But on top of that, the derivatives of the trajectory as a function of the initial conditions, that's all coded up so that basically the partial derivatives of the observables with respect to initial conditions are available. And so then Levenberg Marquardt is pretty straightforward.
Cool, thank you.
Yeah, I've just got a couple of software engineering comments and questions. The first one is, I know Fortran. I did for many, many years, but I was kind of curious, your ChatGPT conversion story, did you use that to convert some of the old Fortran, or was it kind of ground up rewrite?
No, it was so that one, I mean, that was Kevin Napier who did that. He had written ground up Gauss's method in Rust, which is a very new language, and he took that and and I don't know exactly what his query was, but it was from Rust to C++.
Okay.
And it was astonishingly good because, in my opinion, because the Rust has this can return sort of optional results where you either got an answer or the equivalent of no answer. And I was unaware that there's an optional extension, in C++, but ChatGPT was fully aware. And that, so that's what that's the thing that I love.
That's remarkable.
All right, we have a question from Gary in the chat. Are non-gravitational accelerations built in? And oddities like hyperbolic orbits or close encounters? Yeah,
so assist does allow for non-gravitational forces. I have not yet, and the partial derivatives with respect to the parameters of the non-gravitational forces also exist. I've not put that into I have not completely plugged that into the fitting yet, but the bits are there in assist to support that. Likewise, close encounters are handled natively. I mean, that's like the integrator deals with is a adaptive time step stuff, so it can deal with close encounters without a problem. And I guess the other question was hyperbolic orbits. Yeah, so there's the fitting is done in a barycentric Cartesian equatorial frame, and that's really because the positions of the planets and other perturbers in the JPL ephemeris, those files that's in that frame, but there's nothing internal to the code that depends upon orbital elements, and nothing is required to be bound as part of the fit.
Great. I kind of selfishly want to ask what kind of considerations you've had to fold in for handling comets. It's related to non-gravs, I suppose, but just there in general.
Yeah, that's the same. Very similar thing is so the non-gravitational forces are available. What hasn't really been done is the work on sort of splitting up the data from, say, one apparition to another, if that's necessary. That's going to be something that I would hope that you and Carrie Holt and others can help guide me through. Like, I can help you get the fits done, but some of the phenomenology I'm not going to be the expert in. But it'll definitely, I don't see any kind of problem with, I don't see any dynamical showstoppers, and LAYUP is written in a way that's flexibly enough that we should be able to do all of that.
Great. We have a question from Ben in the chat. It sounds like the convert part might be able to translate array data like arrays, dex, times, and uncertainties directly to ADS formatted output. Is that right?
That is the hope. Yeah.
And maybe you could just briefly say for the general audience what ADS is, the ADES format.
Yeah, so ADS stands for what is it? Astronomical Data Exchange Standard is an XML format that is, I think it's been in development for maybe 8 years now, maybe. It does incorporate a lot more information than the older MPC format. I guess Meg is raising her hand, so maybe she can elaborate.
Nope, I was going to ask a question.
Oh, okay.
You're the expert on ADS.
I was going to hand that off to you. So ADS is basically filling the gap of the the old 80 character format. Just really didn't leave enough space for astrometric uncertainties and other auxiliary information, and so ADS is XML, and it's pretty extensible. So then there's a concern about making sure that we're dealing with the data in both directions.
Okay, and it's newer than the 80 column punch cards for sure.
A little bit, yeah.
Yeah. All right, Meg, go ahead.
Well, selfishly, because Kat is here, on a slide that I wrote, we talked about briefly that one of the icing on the cakes thing would be is that we get an orbit fit, and then we're like, what the hell is it? And so since Kat is here, maybe it's a good opportunity to ask Kat and Matt, do you think that's, what would be the synergies there or things needed to make that happen? Because ultimately we get an orbit and then we're like, well, what is it? Next step of things. And I could see that being really useful to users of being able to fit something or ask questions about what does that orbit actually mean? So I'm just wondering if either of you have comments or thoughts about that.
So I can go for a little bit and let Kat take over. So one thing that LAYUP will do, because Hanno has provided this, is that the assist integrator that is under the hood is confined in time to the span of the JPL ephemerides. So if, and that can be thousands of years, but for some of the long-term integration and classification stuff, you want to be able to integrate longer. And so we have the capacity to basically get to the end of the ephemeris and say, well, here are the planetary positions and their masses, and you can just go ahead and numerically integrate the whole thing for however long you want, and then go through the various steps of classifying, is this a centaur? Is this a TNO? If it's a TNO, is it resonant, non-resonant? And then related to that, because we're doing orbit fitting and we have a covariance, we'll be able to make a sample of initial conditions that are consistent with the observations, either directly from the covariance or doing some kind of Markov chain Monte Carlo sample, and then check to see what fraction of that sample has what dynamical classification. I guess I'll let.
Yeah, and I can jump in here. Basically, if you have a rebound initial condition or just positions and velocities, we are a good way along to having our dynamical classification, easy to use Python code ready to go. I've been working especially on the outer solar system stuff. I am just about done integrating a machine learning classifier so that all you need is position and velocity, covariance matrix, or clones, and it will tell you exactly what the TNO is, whether it's in resonances or not. And then Dallin Spencer has been working on the proper elements aspect of the code, which will be more useful for like the asteroid belt. So same concept, orbit and clones, and get proper orbital elements out of the longer term rebound integrations. So that is definitely something I am looking forward to integrating. So our code is basically set up, and it's rebound based, which should play very nicely with assist once we kind of get those integrated. So that is definitely a goal. I would love to be able to take your orbit fit outputs and just feed those directly into the longer integrations. And the idea again is just make it user friendly. So
it should be pretty straightforward.
Yeah. So that's exciting. Because yeah, the one thing that we said we would not touch was the orbit fitting, because that is a whole separate problem. So I'm very happy that you're doing that.
Likewise, I'm happy to hand the classification stuff off to somebody else.
Yeah, and it'll all play nicely together in the end. So it'll be good.
Gary.
Yeah, so speaking of handing things off, so the code you're talking about assumes that the linking job is already done. Is that the case?
Right. This is you. Well, you handed a set of observations. It's going to assume that they are of the same object, and the solutions. It's either going to converge with nice residuals, and you'll say, okay, those observations went together well, or it's going to not. It's going to converge but have really bad residuals, and you'll say, okay, that was a bad link.
And a different question is, how many orbit fits a day or per whatever unit of time you want will LSST need to be doing?
So I'm going to ballpark it here. So I think there's going to be 5 million things that LSST will discover, or in total at the end of the survey. And obviously they won't all need to be fit every day. So I would say, divide that by 100 or 200. And that's probably how many per day need to be done.
Okay. So if you decided, oh, I want to refit everything that LSST found, you're doing millions of things. So this is probably not a giant cluster job. You haven't had to worry about multi-processors or too much in this task.
Not yet, but we're in the middle of the incubator, and that, how to make sure that we're structuring it so it scales up nicely is one of the big questions. But we are, right now it is kind of one object at a time.
Great, thanks.
Yeah, and keeping in mind a lot of the discovery is going to be happening in that first year, so that's going to be an intensive window. So Meg, go ahead. Oh, sorry, Matt.
I was just gonna add to what Gary was saying, that a lot of the work as LSST goes on is going to be about updating orbits, and that ends up being really, really fast, because basically if you have a really good initial guess, and it literally takes in one iteration to get an update.
So mine's more of a comment than a question, but just to say that we've already got some parallelization already in place for basically a structure that works for all the kind of verbiages that we have within LAYUP. So, you know, we can be using the fact that we have multiple cores, right? So even though it is doing one object at a time, right? Again, making sure that we're using all of the available cores. So again, the fact that you can scale it up to use it on a HPC as needed. So I think that's useful that we've already got sort of a logic there. We can see if we need more than that, right, I need to do some more clever things in there, but at least we're at least thinking about, you know, making use of all the core that are available, right, in terms of processing.
Yeah.
And so Rubin Solar System Processing doesn't seem worried, given that that ability exists for them when they think about using this for their data releases.
Adding just a little bit to that, that's how some of the things that are kind of time consuming to compute, like where the observatory is surprisingly, you know, can be a heavy calculation, but that all gets cached because we've got lots of observations from the same time. So there are, like as Meg was saying, there's various things that have already been done to make the parallel calculations more efficient.
Awesome. Thanks very much. Well, it looks like we're coming to the end. Matt, if I could ask you to stop sharing for a moment, that'd be great. Great, thank you. Yeah, so thanks again, Matt, for this awesome talk, and thanks for everyone for attending the Tech Talk series today. Our next talk is going to be on May 8th, 2025, and we'll be joined by Amanda Wasserman from the University of Illinois, Urbana-Champaign, who's going to talk to us about their LINCC Frameworks Incubator called RESPECT, a recommendation system for spectroscopic follow-up. In the interim, please join the LSST DA's LINCC Tech Talk Slack channel and the link at lists.lsst.org mailing list for more information and announcements. There's more information, including links to the Rubin Community Forum and other spots at the LSST Discovery Alliance website. And LINCC Frameworks is holding office hours every Thursday at 10 a.m. Pacific, except for when it conflicts with this talk. And if you have an idea for Tech Talk, we'd love to hear from you. Please reach out to me or to Midai at the LSST DA Slack or email, which is listed also on the Tech Talk webpage. And again, with permission, today's Tech Talk is going to be available on the YouTube channel, ideally within the next few days. Thanks again, everyone, for joining us, and have a great day. Thanks.